Have you ever looked at a math equation and just wondered how in the world it turns into one of those complex curvy graphs? Well, today we are cracking that very code. We're going to dive into graphing polynomial functions. And I know they can look intimidating, but it's really just a puzzle. And the solution? Surprisingly simple. Let's get right into it.
Okay, just look at this curve for a second. It's got these hills, these valleys, and its arms shoot off in totally different directions. How on earth are you supposed to know how to sketch this just from an equation? Honestly, it looks like a secret language, right? But stick with me, because by the end of this, you are going to be fluent. So how do we do it? Well, think of it this way. Every single polynomial graph has to follow a hidden set of rules, kind of like a secret code. And once you know that code, you can predict the basic shape of pretty much any polynomial graph. It's all about just knowing what to look for.
And you know what the best part is? We only need 3 clues. That's it. Just 3 simple pieces of information that are hiding in plain sight right inside the function's equation. And those 3 things will tell us everything we need to sketch out the graph.
All right, let's start digging for our first piece of evidence. This one is the foundation for everything else we're going to do. And it comes from just 2 numbers, the degree and the leading coefficient of the polynomial. So, let's do a super quick refresh. A polynomial function is just one of those expressions with variables and coefficients. But for what we're doing, the single most important part is that highest exponent. We call that the degree. And that little number, that's our master key.
Okay, so here's the deal. When you first look at a polynomial, you want to immediately find 2 things. First, the degree, that biggest exponent you can find. And second, the leading coefficient. That's the number attached to the variable with that highest exponent. These 2 together are our first major clue.
Now let's grab our second clue and see how this all starts to connect. This one is called end behavior, and I love this idea. It's like knowing how the story of our graph begins and ends. It tells us exactly what the graph is doing way out on the far left and far right sides.
So the technical definition of end behavior is what happens to the function as x gets infinitely huge in either the positive or negative direction. But let's be real, a simpler way to think about it is just where are the arms of the graph pointing? Are they both going up, both down, or in opposite directions?
Now this is where it gets really cool, because our first clue tells us exactly what our second clue will be. The degree and the leading coefficient dictate the end behavior every time. If the degree is an even number, the arms point the same way. If it's odd, they point in opposite directions. It is that predictable. And that's incredibly powerful, right? Just by glancing at an equation, you can know if a model is predicting something will grow forever or eventually fall back down. Okay, so we know where the graph starts and where it ends. But what about all the drama in the middle? Well, that brings us to our third and final clue, the turning points. These are the plot twists of our story, the hills and the valleys that give the graph its unique shape. And a turning point is pretty much what it sounds like. It's a spot where the graph just decides to change direction. It stops going up and starts going down, or the other way around. You might know them as local maximums or minimums, the very top of the peaks and the very bottom of the valleys. And this is where it gets so important in the real world, you know? A turning point could be the exact moment a company hits maximum profit, or the lowest point in a patient's fever. So how many of these little plot twists can our graph actually have? Is it just random? No way. There's another super simple rule, and it connects right back to our very first clue, the degree. The maximum number of turns a graph can possibly have is always n minus 1. That's it, where n is the degree of the polynomial. So if you have a polynomial of degree 4, it can have at most 3 terms. A degree of 5 polynomial can have at most 4 terms. It just shows you how beautifully all these clues are connected to each other.
Okay, team, we've gathered all our evidence. We have our 3 clues. Now it is time to put them all together and crack this code once and for all.
So here's the game plan every time. First, find the degree and leading coefficient. Second, use those 2 things to figure out the end behavior. Where are the arms pointing? Third, calculate the maximum number of turns with our little n-1 rule. And finally, you just connect the ends with a smooth curve that has about the right number of twists in the middle. And boom, you've just sketched a polynomial.
So, let's wrap this up. Here is your complete code-breaking kit. The degree is the real MVP. It tells you the maximum number of turns. And with its partner, the leading coefficient, it reveals the end behavior. The end behavior sets the stage, and the turning points, well, they create all the action in between.
So let's go all the way back to the beginning. These curves, they aren't just a bunch of random lines anymore, are they? They're telling stories. the path of a roller coaster, the crazy ups and downs of the stock market, these can all be modeled by functions just like these. So now that you can read the code, what other stories do you see hiding in the world all around you?